Imagine trying to study something that the universe literally refuses to let you see on its own. It's a mind-bending cosmic puzzle, right? I mean, we know these fundamental particles exist, but the strict laws of nature dictate that we can never, ever isolate one. Welcome to our explainer today. We're going straight to the heart of matter to unravel one of the absolute most bizarre, yet totally fascinating mysteries in all of modern physics.
Now you might be wondering, why should we care about things we can't even see? Well, because the invisible interactions between these particles, quarks and gluons, are responsible for almost all of our perceived mass. Yeah, you heard that right. The unseen dynamics we're about to explore are literally where we get our physical mass. Without this chaotic, microscopic dance happening at the subatomic level, you, me, the Earth, the stars, we essentially wouldn't even have weight. It's wild to think about.
So, the roadblock here is a phenomenon known as color confinement. Think of it as the ironclad rule of the strong nuclear force. It basically dictates that quarks and gluons can never be isolated. They're permanently imprisoned, totally forced to remain bound inside composite particles. If you try to pull them apart with incredible force, the energy you put into it just creates more quarks. It's an absolute wall for physicists. You literally cannot get a single quark on its own in our universe today.
Okay, so let's dive into the framework that actually makes sense of all this. Our explainer today is titled The Invisible to the Exotic, Decoding Quantum Chromodynamics. We're going to take what looks like a totally impenetrable theory of physics and turn it into a real-life detective story. We'll see exactly how scientists use brilliant math and massive supercomputers to study the unseeable, calculate the impossible, and even discover entirely new forms of matter. Here's our roadmap for the journey today. We'll start with the quark confinement paradox. Then, quantum chromodynamics explained. Next up, simulating the lattice. Then we'll cover hadron spectroscopy. And finally, we'll wrap up with hunting exotic particles.
Let's kick things off with Section 1, the quark confinement paradox. This specific paradox is what kicked off decades of intense physics research, and it totally revolutionized how we view atomic structure. Look at the stark contrast in these extremes. When you have high energy, which physicists call asymptotic freedom, and quarks are incredibly close together, they're virtually free. It's almost like they don't even notice each other. But at low energy, as you try to pull them apart, the strong force acts exactly like a giant rubber band, snapping back with immense strength. This creates a non-perturbative puzzle where all our traditional mathematical tools just completely break down.
Moving on to Section 2, Quantum Chromodynamics Explained.
So quantum chromodynamics, or QCD for short, is the definitive theory of this strong interaction. And it's built around a pretty diverse cast of characters. We've got 6 distinct quark flavors. You have the lightweight up and down quarks, all the way to the incredibly massive top quark. They have these weird fractional electric charges, and they interact by tossing force-carrying particles called gluons back and forth. These gluons carry what we call color charge, which is this highly complex quantum property driving the symmetry that binds all matter together.
Let's jump to Section 3, Simulating the Lattice.
Because our traditional math falls apart at low energies, physicists needed a completely out-of-the-box approach. Enter lattice QCD. Basically, we chop continuous spacetime into a digitized 4-dimensional grid. And to solve the physics on this grid, we use a Monte Carlo algorithm running on massive supercomputers. It's a 3-step loop. First, generate random link variables on that grid. Second, compute the change in the system's overall action. And third, accept or reject the configuration based on quantum probability. By running this loop literally millions of times, we can explore a vast landscape of probabilities and finally calculate those low-energy strong interactions.
That brings us to Section 4, Hadron Spectroscopy.
Now, with our supercomputing grid up and running, we can translate all that math into real-world particle analysis. Look at the static potential energy graph here. It brilliantly illustrates the proof of confinement on the lattice. Notice how the energy rises in a straight line the further out you try to pull the quarks. The further they get, the more energy it takes. It's definitive proof they are permanently confined. And then over on the correlation functions graph, see those flat plateaus? That is exactly where scientists can accurately extract the effective mass of a bound particle state. So through these simulations, we are virtually weighing particles that we can't even see isolated in nature. How cool is that?
And finally, Section 5, Hunting Exotic Particles.
So what actually happens when quarks group together in ways that completely defy traditional textbooks? We usually think of quarks grouping in 2s or in 3s to form things like protons and neutrons. but the math of QCD doesn't actually forbid other, much wilder combinations. Through hadron spectroscopy, scientists are actively hunting for these exotic hadrons. We're talking about tetraquarks, bizarre configurations of 4 quarks, pentaquarks made of 5, and maybe the strangest concept of the whole shebang, glue balls. These are hypothesized particles made entirely of interacting gluons, without a single quark inside them. Finding these states pushes the absolute boundaries of the standard model of physics.
And here is the incredible visual payoff. We aren't just theorizing about these anymore. What you're seeing here are actual experimental data plots from major particle colliders like Bell, BES3, and LHCb. They show the real-world discovery of exotic candidates, particles known as the X, ZC, and TCC. Look at those peaks in the data. That right there represents experimental confirmation. We are actively confirming the existence of tetraquarks containing multiple heavy charm quarks, proving that these exotic configurations are very, very real. It's this beautiful moment where decades of theoretical QCD and lattice supercomputing have finally converged with experimental physics to discover entirely new matter.
I really want to leave you with this provocative thought as we wrap up our explainer. If we have just in the last 2 decades begun to discover these exotic 4 and 5 quark states, what other hidden configurations of matter might still be lurking in the complex math of QCD? Our journey from invisible, confined quarks to massive supercomputer lattices proves that the universe still has plenty of profound secrets left to uncover. It's really just waiting for us to build the right tools to look. Thanks so much for joining me today.